In this section, we explore the mole, the concept of the mole, and molar mass, which relates the mass of substances to their amounts that are present in moles. So in this section, we're going to be connecting the atomic and real worlds, that is, the world at the atomic level, which we can't see and can't really measure very easily, with real-world objects and real-world amounts that we can measure. To do that, we use the mole, which is the chemist's way of doing this. And to do that, we use the concept of the elemental molar mass, the mass of a mole of an element, and a compound molar mass, which is the mass of a mole of a compound. And mostly what we'll be doing is looking at the way you convert amounts of atoms, or numbers of atoms, and amounts in units of moles, and the mass in general units of grams. So let's start out. The idea is that what we have is substances that we think about in terms of atoms and molecules as chemists, and those are really, really small. So when we think about water, we think about some water there, and that's a bulk amount of water. You could drink it, although you wouldn't out of a beaker ever, because that's dangerous. But we think as chemists of that water as being a collection of many, many little water molecules, and molecules are so small you can't see them. Likewise, a diamond is made up of carbon atoms connected together in a particular arrangement, and we think about diamond as chemists, as those atoms and the way those atoms hook together, but you can't really see those atoms. What we can see is a bulk diamond. Same thing for another form of carbon, graphite, which is sheets of carbon atoms, and a similar idea for the compound quartz, which is made up of silicon and oxygen. And so what we do is, because we can't measure individual atoms and molecules, what we do is we have this idea called the mole, which connects these small, tiny things that you can't see with these bulk objects that you can see. And the idea is that a mole of something, a mole of most compounds and most elements, is roughly a small handful. It's about the size that you could fit in your hand, more or less. And so it's a real-world, easy-to-grasp amount, but it's representing a number of particular things that are not easy to grasp because they're so small. And that number is called Avogadro's number. And so a mole of anything is 6.02 times 10 to the 23rd of those things. It's like a dozen is 12 things, a pair is 2 things, a mole is this number of things. And so you can have a mole of atoms or a mole of molecules. And so this picture here shows a mole of a few different elements and a few different compounds. So the elements are copper and aluminum and sulfur, and the compounds are potassium dichromate and water and copper 2 chloride dihydrate. So let's look at the elements first. The idea of the mole is that this sample of copper contains 1 mole of copper. It contains 6.02 times 10 to the 23rd atoms of copper. This sample is a mole of aluminum. It contains 6.02 times 10 to the 23rd atoms of aluminum. This is a sample of sulfur. It contains Avogadro's number, 6.02 times 10 to the 23rd atoms of sulfur. Looking at the compounds, let's look at water first. This is a sample of water. It contains 1 mole of water, which means it contains 6.02 times 10 to the 23rd water molecules. Remember, the water molecule has the formula H2O. So what that means is each molecule has 2 hydrogens and 1 oxygen atom. So that means that this sample, which contains 1 mole of water molecules, contains twice that number of hydrogen atoms, because each molecule contains 2 hydrogen atoms. Kind of like if you had a person, if you had a pair of people, 2 people, you had a pair of people, you'd have a total of 4 arms, because each person has 2 arms. It's just like that. Potassium dichromate, a mole of that contains a mole of potassium dichromate units, which means it would have 2 times Avogadro's number of potassium atoms, and, for example, 7 times Avogadro's number of oxygen atoms. The most important thing about Avogadro's number is it acts as a conversion factor between moles and numbers of atoms or numbers of molecules. And we'll look at this in terms of atoms of an element. So 1 mole is 6.02 times 10 to the 23rd atoms of that element. And the idea is you can use that to convert between moles and atoms, or between atoms and moles. So we'll start out looking at a sample that is 1.95 moles of aluminum, and we ask ourselves, how many aluminum atoms are in that sample? Well, if you know you have numbers of moles, the idea that 1 mole is equal to that number of atoms, that becomes a conversion factor. Because these two things are equivalent, you can make a fraction out of them, where that fraction is essentially the number 1, because the thing on the top and bottom are the same. But when you multiply through, the units of moles of aluminum cancel, and you end up with units of atoms of aluminum. And so when you multiply the 1.95 times the 6.02 times 10 to the 23rd, you come out with 1.17 times 10 to the 24th atoms of aluminum. So we've taken a sample, and we knew what it was in terms of the moles of aluminum, and we've converted that to the number of atoms of aluminum. It hasn't changed the sample. It's the same sample. We're just describing it in different units. Likewise, you can take a sample for which you know the number of atoms. This is far less likely to be the case, but you could do it, for which you know the number of atoms, and you can convert that to the number of moles, or the amount that's present in moles. And so we'll do this for copper. We have 4.68 times 10 to the 23rd copper atoms in this sample the person's holding. And what we do is we use Avogadro's number as a conversion factor, but this time we set it up with moles on the top and atoms on the bottom, because we want to get rid of the units of atoms, and we want to come out with units of moles. So we end up with moles of copper, and when you divide that out, you come up with 0.777 moles of copper atoms. So the idea is that this Avogadro's number can be used to convert from moles to atoms, or from atoms to moles, and likewise for molecules. Here's a question. When doing these calculations, does it matter which element is used? Does it matter if it's copper or aluminum or titanium? And the answer is no, because Avogadro's number is just the number of atoms. It doesn't say anything about what those atoms are like, any properties of those atoms. So when converting between numbers of atoms and the amount that represents in moles, it doesn't really matter what element you're talking about. Later on, when we talk about mass, it will matter, because then the different atoms might have different masses. And let's move on to that. So the next idea is the idea of molar mass. So a mole is a collection of atoms of a particular number of those atoms. Elemental molar mass is how much does that weigh, essentially? What's the mass of that number of atoms of a particular element? And conveniently, these are listed on your periodic table in units of grams for 1 mole of that atom. So the idea on your periodic table is, if we look at the blown up one here for uranium, a mole of uranium has that equal to it, that's its atomic weight in atomic mass units, but it's also the mass in grams for 1 mole of uranium atoms. Avogadro's number of uranium atoms has a mass of 238.0289 grams. And so each element has its own average molar mass, or combined molar mass. So we'll look at a blown up one here. So for example, boron has a molar mass of 10.811, which means 6.02 times 10 to the 23rd atoms of boron has that mass in grams. So if we look at aluminum, it has an atomic weight of 26.9815, so that means 1 mole of aluminum atoms has a mass of 26.9815 grams of aluminum. Likewise, fluorine has 18.9984 as its listing for molar mass or atomic weight on the periodic table, so that means 1 mole of fluorine has that mass. Molar mass is generally thought of as having units of grams per mole. So those are just listed on your periodic table. The idea of molar mass is that it can be used as a conversion factor between mass and moles. That's its purpose. That's what it's used for, and it's incredibly important. You use it all the time. So look at aluminum as an example. 1 mole of aluminum has a molar mass of 26.98 grams of aluminum. Because those two are equivalent, you can make a fraction out of them where you're essentially using as a conversion factor, because you'll be multiplying some initial quantity by the number 1, and you can do that 2 ways. You can put the grams on top, the moles on bottom, or you can put the moles on top and the grams on bottom. And depending on what you want to do, you'll use these 2 different forms. So let's look at a couple of examples. Let's start out by saying we have our example before of 1.95 moles of aluminum, and we want to know what's the mass of that in grams. And so what we have to do is we have to choose one of these two conversion factors to get us from units of moles to units of grams. And the one we want to choose is the one with grams on top and moles on the bottom, because that will eliminate, that is, cancel the units of moles and give us units of grams, introduce units of grams, without changing the amount of aluminum that's actually present, because these two things, top and bottom, are equivalent to each other. So units of moles cancel, and we end up with units of grams. And that comes out to 52.61 grams. Notice I've used the molar mass for aluminum only to 4 significant digits, or more importantly, 2 decimal points, 2 decimal places. We generally use, for most purposes in this course, molar masses to 2 decimal places. Okay, let's look at the opposite example. We have this sample of copper, 49.4 grams, and we want to know how many moles is that? What's that amount in moles? So we're going to multiply that by something, and we want to end up with moles of copper. And looking on periodic table, the molar mass, the atomic weight of copper is 63.55. We have 2 conversion factors we can choose from. We want to choose the one that gets us moles and gets rid of grams, so we choose this one. So it's 1 mole over 63.55 grams of copper. And that's 0, as we saw before, 0.777 moles. So those are 2 of the most important conversions you'll have to do, and you'll do them over and over again. That is, going from moles to grams using molar mass, or going from grams to moles using molar mass. There'll be plenty of others, but these are 2 of the very, very most important. How important? Very important. Now let's go to the next level of complication and talk about this in terms of compounds, that is, things made of more than one atom and of different elements, and talk about molar mass and use of that for compounds. The compound molar mass is the mass of Avogadro's number of molecules. It's also then the sum of the atomic weights from the periodic table of the atoms that make up those molecules. So let's look at an example of SO2. SO2 contains 1 sulfur and 2 oxygens, so the molar mass is the mass of 1 mole of sulfur plus the mass of 2 moles of oxygen. The mass of 1 mole of sulfur we get from the periodic table, it's 32.066 grams. Oxygen is going to be 2 times, well, that's a crummy 2 times 15.9994 grams. And when we do that out, we come out with 64.06 grams per mole of SO2. So the molar mass of SO2 is 64.06 grams per mole. And we do that by adding up the numbers. Note, of course, that you need to use the number of atoms in the molecule, not simply the listing up. You wouldn't, for example, just add 15.9994 plus the 32.066. You have to account for the fact that there are 2 oxygens there. Okay. When you're converting between grams and moles for a compound, that is using the molar mass, you of course have to determine the molar mass of the compound first, and then use the molar mass as a conversion factor, as we saw a minute ago, for atoms, for elements. So let's look at an example of going from moles to grams for SO2, and we had our SO2 molar mass, which we just figured out, 64.06 grams per mole. And so what's the mass of 1.45 moles of SO2? So what you would do is take the 1.45 moles of SO2, and we want to convert that to grams. So we'll use our conversion factor of 1 mole of SO2 on the bottom and 64.06 grams of SO2 on the top. That way moles cancel, and we end up with grams. 1.45 times 64.06, 92.89 grams of SO2. Now let's look at the next example in the opposite direction, going from grams to moles. What's the amount in moles of a 212 gram sample of SO2? So we have 212 grams of SO2, and we want to convert that to moles. And so what we want is we want grams on the bottom, so the 64.06 grams of SO2 is on the bottom, and the 1 mole of SO2 is on top, and that way grams of SO2 will cancel. And we have 212 divided by 64.06, and we end up with 3.309. Nope, 3 significant figures, my friends. 3.31 moles of SO2. Actually, this one up here, I just realized, should be 92.9 grams of SO2 because we had only 3 significant figures. One thing that you'll see a lot of as you progress further in sciences in general and chemistry in particular are things for which you need to string different conversions together in a multi-step problem. So here's an example where we ask how many oxygen atoms are present in a 212 gram sample of SO2. And the way to start approaching these is to get in the habit of drawing a problem map where you kind of take what you know and what you want to find out and kind of link them together just kind of conceptually before you actually do any math. So we have grams of SO2, and what you think about is, well, what can I convert that into? I can convert that into moles of SO2, because I can use the molar mass to do that. From moles of SO2, I can convert that into moles of oxygen, because I know there's just 2 oxygens for each SO2, and from moles of oxygen, I can go to atoms of oxygen. So that's a good way of doing this problem. And so each of these will be one different calculation, one different conversion that we would have. So this first step here would be 212 grams of SO2, which we just did a minute ago, times 1 mole of SO2 divided by 64.06 grams of SO2, and that would give us to 3.31 moles of SO2. Then what we do is we take 3.31 moles of SO2 and we convert that to moles of oxygen. And we know that there are 2 moles of oxygen for every 1 mole of SO2. And how do we know that? Because of the formula. The formula says there are 2 oxygen atoms for each sulfur atom. So therefore each mole of SO2 will have 2 moles of oxygen. So that's then 6.62 moles of oxygen. That was the second one here. Second step. And our final step will be converting from moles of oxygen to atoms of oxygen. 6.62 moles of oxygen times Avogadro's number, 6.02 times 10 to the 23rd, atoms of oxygen for each 1 mole of oxygen. And that comes out to 3.98 times 10 to the 24th oxygen atoms. And so always start by making up a little problem map and then go ahead and do the calculations.